Mind-controlled prosthetics represent a significant advancement in biomedical engineering, merging the fields of neuroscience, robotics, and materials science to create a system that can be controlled by the user's thoughts. Here's an extensive explanation of their technical aspects, functionality, and applications. Technical aspects. Mind-controlled prosthetics are designed to mimic the natural movement of limbs by integrating with the user's nervous system. The key technologies involved include osseointegration. This is the direct attachment of the prosthetic limb to the skeleton, providing mechanical stability. Neuromuscular cuff electrodes, implanted around the main nerve bundles in the arm. These electrodes pick up electrical signals from the nerves that used to innervate the missing limb. Regenerative peripheral nerve interface. RPNI, a small graft of muscle tissue, is attached to the end of a severed nerve, promoting healthy nerve growth and acting as a bioamplifier for neural signals. Functionality. The functionality of mind-controlled prosthetics is based on capturing the electrical signals generated by the brain and translating them into movements. Signal capture. The user's intention to move is translated into neural signals that travel down the nerves to the site of amputation. Signal amplification. The RPNI amplifies these faint neural signals into larger, recordable muscle signals. Signal interpretation. An embedded control system interprets these signals and translates them into precise movements of the prosthetic limb. Feedback loop. Tactile sensors on the prosthetic can send signals back to the brain, allowing the user to feel sensations from the prosthetic limb. Applications. The applications of mind-controlled prosthetics are vast and transformative, particularly for amputees' daily activities. Users can perform complex tasks like gripping objects, typing, or using tools with precision. Sensory feedback. The ability to feel textures and pressure enables users to perform delicate tasks like handling fragile items without visual aid. Medical rehabilitation. These prosthetics can be used in rehabilitation to improve the quality of life and independence of amputees. Research and development. Ongoing research may lead to further advancements, such as full limb replacements that can be controlled with the same dexterity as natural limbs. In summary, mind-controlled prosthetics are a groundbreaking technology that restores not only the function but also the sensation of lost limbs, significantly improving the lives of amputees. They stand as a testament to the incredible potential of integrating technology with human biology. Comparison of mind-controlled prosthetics versus traditional prosthetics. Mind-controlled prosthetics differ significantly from traditional prosthetics in several key aspects, including their integration with the user's nervous system, functionality, and the level of control they offer. Here's a comparison. Integration with the nervous system. Mind-controlled prosthetics. They are directly integrated with the nervous system via implanted electrodes, allowing for more natural and intuitive control. Traditional prosthetics. Typically, they are not integrated with the nervous system and rely on mechanical systems like straps or harnesses for control, functionality and control. Mind-controlled prosthetics. These prosthetics can be controlled by the user's thoughts, allowing for accurate movement regardless of limb position and refined manipulation of objects. They also enable the experience of different sensations for various textures. Traditional prosthetics. They generally offer basic functionality and are controlled by the remaining part of the limb or other body movements, which can be less precise and may not allow for sensory feedback. Sensory feedback. Mind-controlled prosthetics. Users can experience sensations of touch, which is a significant advancement over traditional prosthetics. This sensory feedback allows for more precise and dexterous use of the prosthetic limb. Traditional prosthetics. Sensory feedback is typically absent, which means users cannot feel textures or the force they are applying, making delicate tasks more challenging. Daily use and adaptation. Mind-controlled prosthetics. They are designed for everyday use and can be adapted to professional and personal activities, providing a level of autonomy and functionality that closely resembles that of a natural limb. Traditional prosthetics. While they can restore some level of function, they may not offer the same degree of freedom and adaptability as mind-controlled prosthetics. In summary, mind-controlled prosthetics represent a leap forward in prosthetic technology, offering users a more natural and intuitive way to control their prosthetic limbs, along with the ability to feel sensations, which greatly enhances their overall functionality and user experience. Traditional prosthetics, while still useful, do not provide the same level of integration or sensory feedback. The limitations of mind-controlled prosthetics. Mind-controlled prosthetics, while revolutionary, do come with certain limitations. Here are some of the main challenges and constraints associated with these advanced devices. Cost. Mind-controlled prosthetics are currently very expensive, with prices reaching up to $8 million US. This creates a significant financial barrier for many potential users. Surgical risks. The integration of these prosthetics often requires invasive surgery to implant electrodes and other components. This can pose risks of infection, rejection, and other surgical complications. Technological complexity. The systems involved are highly complex and require a multidisciplinary team for maintenance and troubleshooting, which can limit accessibility and widespread adoption, durability, and maintenance. These prosthetics contain delicate electronic components that may require regular maintenance and can be prone to malfunctions or breakdowns. Cognitive effort. The control strategies for mind. Controlled prosthetics can be unnatural and unintuitive, requiring significant cognitive effort from the user. This can result in poor naturalness and fluidity of movements, limited sensory feedback. Although mind-controlled prosthetics can provide some sensory feedback, it is often not as rich or as nuanced as the natural sensations experienced with biological limbs. Psychosocial factors. The use of such advanced technology can blur the lines between humans and machines, raising ethical and social questions about identity and the definition of being human. Compatibility and customization. Each prosthetic must be custom-fitted and programmed to work with the individual's unique neural and muscular system, which can be a time-consuming and complex process. Battery life. The prosthetics rely on battery power, which means users must manage charging cycles and may face limitations in usage duration. Learning curve. Users must undergo extensive training to learn how to control the prosthetic effectively, which can be a lengthy and sometimes frustrating process. Despite these limitations, ongoing research and development are continuously addressing these challenges, aiming to make mind-controlled prosthetics more accessible, affordable, and user-friendly. As technology advances, we can expect many of these limitations to be mitigated or overcome entirely. The recent breakthroughs in mind-controlled prosthetics have been quite remarkable, pushing the boundaries of what's possible in bionic technology. Here are some of the most notable advancements. Restoration of touch. Researchers have made significant progress in restoring a sense of touch to prosthetic users. An experimental research project funded by the Defense Department and Veterans Affairs has enabled an amputee to feel his wife's hand using advanced prosthetic technology. This system uses electrodes implanted in muscles to pick up brain signals for movement, which are then translated to the hand. Sensors in the prosthetic fingers connect back to nerves in the arm to return a basic sense of touch. Neuromusculoskeletal prostheses. For the first time, people with arm amputations can experience sensations of touch in a mind-controlled arm prosthesis that they use in everyday life. This new technology is one of the world's most integrated interfaces between human and machine, where the prosthesis is connected to the user's nerves, muscles, and skeleton. The research has shown that these prostheses can operate much more precisely than conventional prosthetic hands and have improved the use of the prosthesis by integrating tactile sensory feedback, finger-level control. University of Michigan researchers have tapped faint, latent signals from arm nerves and amplified them to enable real-time, intuitive, finger-level control of a robotic hand. This breakthrough has closed the gap between amputee patients thinking about moving a prosthetic limb and the limb actually moving. A brain signal amplification for control. Scientists have developed methods to amplify the faint signals from the brain to control individual fingers on a prosthetic arm. This advancement allows for more precise and nuanced control of the prosthetic, making it possible for users to perform more complex tasks with their artificial limbs. These breakthroughs represent a leap forward in prosthetic technology, offering new levels of independence and quality of life for amputees. The integration of sensory feedback and precise control mechanisms are particularly transformative, allowing users to interact with their environment in ways that were previously impossible.